All right, so let's review the exam 2 questions here. All right, so for F session, since we have already done with the multiple choice questions, you can just escape the first part and then you can continue. All right, for G and H session, let's get started. All right, okay, so for the exam 2, right, so the topics will only focus on the regression, right? So simple regression, multiple regression, right? Okay, so then let's talk about the first question, right? When a predictor is added to a regression model, the R square will, and adjusted R square will, right? So here in this case, we say when we when we compare models, right? So we say we never use R squared to compare models. Instead, we use the adjusted R square to compare models. Why is that? Still remember, we say when we add a predictor into the regression, the R square will always increase. Right? It doesn't matter this added predictor is useful or not useful. R square will always increase. That's why when you use R squared to compare models, it is not fair for the models, right? Even though you add a lot of unuseful predictor to the regression, the R squared getting larger, it doesn't mean this model is better, right? So we say we use the adjusted R squared because R squared sometimes increase because you add a very useful predictor. But the other way, if you add a very unuseful predictor into the regression, the adjusted R squared will decrease, right? So then in this case, which option will be A, right? So R squared will always increase, but adjusted R squared will sometimes increase depending on what kind of predictor you add into the regression. All right, okay, so then number 2. In the jump regression analysis, the RMSE, which is the root mean square error in the output, is referring to the, right? So it is standard deviation of the residuals, square root of the variance of y, variance of the model, or variability in the observed y values. Right, so whenever we talk about the RMSE, right, so here I even gave you the whole name of RMSE. You can see that RMSE is about the air, right? So which of the following is talking about the air? The residuals, right? So this is the first idea. But if you look at our formula sheet, we do have a formula for root MSE. All right, so the square root of MSE is just the standard deviation of the residuals. All right, so this is about the root mean square error, right? So then the answer will be A. All right, so it's nothing about the y, it's actually about the difference between the observed y and the predicted y. It's actually about residuals. All right, okay, so then number 3. In a multiple regression, a linear relationship exists between the response variable and the explanatory variable, but the residual plot shows a cone shape. Then what should we do next? All right, so then in this case, the first sentence, we say a linear relationship exists between the response and each explanatory variable. So this sentence tells us about what? It means our linearity assumption is good, right? But a residual plot shows a cone shape, so that we use the residual plot to check the equal variance assumption, right? So we say for equal variance assumption, we look at the residual plot and we expect the residuals to be equally distributed around the zero line, right? So if this residual plot shows a cone shape, that means the equivariance assumption is not satisfied, right? So then what do you need to do next? Of course, next step, we want to fix it, right? We want to fix this problem. Then, can you run an F test? Of course, you can run an F test, but it cannot solve this problem, right? It cannot improve anything. So, what is our option? Try the transformation, right? So, we say in the regression, we never quit because we can always find a way to fix the assumption problem by transformations. All right, so of course we don't want to give up, and it is the same thing if you look for other variables to use, right? You are giving up the previous variables. All right, okay. So then number 4, selling price, All right, so we have a background, and then we have the plot of the residuals versus the predicted values. And we also have a normal plot of the residuals are shown below. So what do the plots suggest? All right, so then in this case, we say, okay, let's look at number A. It says the linearity condition is satisfied. So how can we check the linearity condition? By what plot? By scatter plot, right? So what does the scatter plot look like? It should be the predictor versus the response variable, right? And then we have the points, and then we want to see that whether the points show a linear relationship, right? Okay, so now what do we have here? First, we have the residual plot, right? So when do we use the residual plot? Again, the same idea, right? So we use the residual plot for the equivariance assumption, right? Okay, what about the next one? What about this normal probability plot? Is this a scatter plot? Of course not, right? So then in this case, we say this is about the residuals, right? And then we want to check whether the residuals follow this straight line, even though it is a little bit different format as what you saw in the jump, something like the two curves, right? Sometimes other software doesn't show this curve, but you know this is about the normality, right? So it is not a scatter plot. Even though you can see that the residuals follow the straight line, it is not a scatter plot. So that means we don't know about the linearity condition. Right, so we don't know whether this condition is satisfied or not because we need a scatter plot, but we don't have that for in this question. All right, okay, so then let's continue. Next one, for the normality assumption. All right, so what about the normality assumption here? In this case, we say we have this plot is actually called what? The normal quantile plot, right? So this plot is actually a normal quantile plot. We expect the residuals to follow this straight line. So is this satisfied? Yes, right? So then B is not correct, right? So then number C, the equivariance assumption is violated, right? So we say, okay, we use the residual plot to check the equivariance assumption. We expect the residuals to be equally distributed around the 0 line. So what about this one? It is quite clear cone shape. Right, so then what? That means the equivariance assumption is not good, right? So that means C is correct. What about number D? D says all assumptions are not satisfied because the sample is not randomly selected. We say the sample is randomly selected is for the independence assumption, right? So if the sample is not randomly selected, then independence assumption is not checked. It doesn't mean all other assumptions also not satisfied, right? So that would be C. All right, so let's continue. Number 5, Right. When the scatter plot shows a positive association between the predictor and response variable, the coefficient on the same predictor in the multiple regression analysis will be positive, will be negative, or either. All right, so then in this case, it says a scatter plot, right? So that means a scatter plot between the predictor and the response variable shows a positive relationship. That means when x increases, the y will also increase, right? Okay, so then the coefficient for the same predictor in the multiple regression analysis will be positive, negative, or don't know. All right, so then in this case, if I change this multiple regression to simple regression, then what is your answer? You say if the scatter plot, the relationship between x and y is positive, then in the simple regression, the coefficient must be positive, 100% positive, right? But the question is not asking about the simple regression, it's asking about the multiple regression. So what's the difference between simple regression and multiple regression? The multiple regression have more predictors, right? The predictors affect each other, right? So, for example, in our class, we talked about the house price and the relationship with the number of bedroom and the living area, right? So we talked about this example for many, many times. Right, so then in this case, we say if we only care about the number of bedroom, then what? Then we say the number of bedroom and the house price has positive relationship, right? Generally, when a house have more bedrooms, then the house price will increase. But the other way, now I add the living area into the regression. Then if you still remember, the coefficient of the bedrooms changed to negative because what? Because now, whenever we talk about the coefficient for the bedroom, we need to get everything else fixed, constant, right? So then that means when the living area is fixed, then if you keep adding the number of bedrooms into the room, then the house is not preferred. The house price will decrease. The coefficient for the bedrooms will change to negative. All right, so then in this case, we say in the multiple regression, the coefficient for a predictor is not determined by itself. It is determined by all other predictors. All right, so since we don't know other predictors in this question, right, so we don't know what is the effect of other predictors to this predictor, right? So can be positive, can be negative. We don't know. All right, so then number 6. So now we have a regression equation to predict the job performance of the new hires based on the age, GPA, and gender. All right, so then we say the gender is a kind of a categorical variable with female equals to 1 and male equals to 0. Right, so now we have this equation, and then for gender, if it is male, then gender equals to 1. If it's female equals to 1, male equals to 0. Right, so now which of the following is the correct interpretation for the regression coefficient of this gender variable? All right, so then let's try, right? So if this female, then gender equals to 1, then 9.06, 06 times 1 is just a 9.06, right? But if it is male, then this gender equals to 0, so this whole term will just change to 0, right? So then which gender has better job performance? Will be female, right? So it looks like female is higher than male by 9.06, but is this done? No, because this is a multiple regression, right? So we need to get both of these two predictors fixed or constant. Otherwise, you don't know how to compare the job performance for these two genders, right? So some of you just stop at the first point and chose A, right? But actually, it is not correct. We need to choose D, right? So we say the female is 9.06 points higher than the male, but at the same time, they should have the same age and GPA, right? Get all other predictors fixed or constant. All right, okay, so then let's continue. Number 7. Right, so indicator or dummy variables are used to describe the association between the response variable and a. So this question is easy, right? So why do we need dummy variables? Is because we have a categorical variable and we think this categorical variable will affect the response variable a lot. So we want to change this categorical variable to quantitative variables, right? So that we can study about the effect of this categorical variable. So of course, we want to study about the association between the response variable and a categorical variable. Okay, so number 8. Why shouldn't we use R-squared to compare models? All right, okay, so here in this case, so it can take any value greater than 0, which makes it difficult to interpret. It is not standard output, so can be difficult to obtain. Adding any predictors to a model, even those are insignificant, can still increase its value. Outliers can easily influence the value, make models appear better than they really are. So which one is the reason why we don't use R-squared to compare models? Still remember the first question, right? So we talked about the difference between the R-squared and the adjusted R-squared. We said R-squared will always increase as long as you add a predictor into the regression. It doesn't matter this predictor is a good predictor or bad predictor. It will always increase, right? So actually, which one? Just a C, right? Adding any predictors to a model, even those are not significant, insignificant, can still increase its value. All right, number 9. When modeling the highest education level achieved on the salary analysis, how many dummy variables would be created and added into regression if the options are high school, associate's degree, bachelor degree, master degree, and PhD? So for this question, it's asking about what? It's asking about, okay, so now we have a categorical variable with 1, 2, 3, 4, 5 categories, right? Okay, so now how many dummy variables do we need to create? We say we want to randomly choose one as the base, right? And then what? And then create dummy variables for the other 4, right? So 1 as the base. That means you need to create 4 dummy variables for the other 4 categories. All right, okay, so then number 10, which of the following statement is correct? Right, so if you look at these 4 options, right, so they are all about what? They're all about the correlation coefficient R, right? So then in this case, let's review a little bit for the correlation coefficient R. Right, so we'll say for the correlation coefficient R, right. So the first important property is R is designed to measure the strength of the linear relationship, right? And then we say R has a range from -1 until 1 and with 0 in the middle, right? So we say when r equals to 1, we have the strongest linear relationship, right? And then when r equals to -1, then we still have the strongest linear relationship. But when r equals to 0, then we say there is no linear relationship, right? So then in this case, we say when it is approaching to 0 from two sides, then the relationship is getting weaker, right? So y r equals to 1 and r equals to -1 both shows strongest linear relationship. What's the difference? We say r equals to 1 shows the positive strongest linear relationship. When r equals to -1, that means you have strongest negative linear relationship, right? But both of them shows the strongest linear relationship, right? And what else? We say r has no units, right? So it's just a measurement for the strength of their relationship. So r has no unit. And also we say if you exchange x and y, the r doesn't change, right? And then the last one, we say r is not resistant, right? So we say it can be affected by the outliers a lot, right? So that will be all the properties of the correlation coefficient r. All right, so now let's look at these options one by one. All right, so first one, A. Say if the correlation coefficient r is close to 0, then there is no association between the two variables. Is this correct? What about for this case? In class, we did this example, right? So is there any relationship or association between x and y? Yes, they have strong quadratic relationship. But is there any linear relationship? No. That's why r will be very close to 0, right? So then we say if the correlation coefficient r is close to 0, then there is no linear association. You can only say there is no linear association. There may be some other kinds of association. All right, so A is not correct. Okay, number B. A correlation coefficient r equals to 0.68 shows a stronger linear relationship than r equals to negative 0.89. What about this one? We say when we talk about the correlation coefficient, right, the positive or negative doesn't show the strength of the linear relationship. It only tells you the direction of the linear relationship, right? So then when we compare the strengths, then you just look at the absolute value, right? We don't care about the sign, right? So then in this case, which one is stronger? This one is stronger, right? So then B is not correct, right? So number C, the correlation between school GPA and the IQ score for 57 grades, 7th grade students is positive, then the correlation between the IQ test score and GPA is negative. Let's make it in short. That means the correlation between GPA and IQ is positive, then the correlation between IQ and GPA is negative. No, because we have this property, right? So we say if we change the order, the R doesn't change. It's just like the relationship between A and B is the same relationship as between B and A, right? So it's the same thing. So C is not correct. And then last one, the correlation coefficient R is not resistant. it will be affected by the outliers. That's why we call the correlation coefficient is not a resistant mirror or not a robust mirror. All right, so then D is correct. All right, okay. So then we are done with the multiple choice questions. So let's talk about part 2, written questions. All right, okay, so for the first problem, a sale manager has decided to investigate the idea of performance that can be predicted by GPA, work experience, certification training, and the number of workdays absent. All right, so then the manager fits a regression and the output is provided here. All right, so now I want you to fit in the missing values in the above partial ANOVA output. Okay, so when we look at this kind of, right, so when we look at these values, right, so which one is the easiest one to fill? Normally we start with the ANOVA table, right? So let's review the ANOVA table a little bit. All right, so for ANOVA table, the first column is called the source, right? So then the variance in Y can be from the model, right? And can from the air, right? And also these two sum together, we have a total row, right? And then next column is called the degree of freedom, right? So then we have the degree of freedom for the model is K, right? Degree of freedom for the air in general is n minus 1 minus K. And then these two degree freedoms sum together will be n minus 1, which is the degree freedom for the total, right? So then based on this relationship, we say the degree freedom for the model plus the degree freedom for the error will be the degree freedom for the total. So here is 4, right? Okay, so then next column is called the sum of squares. Alright, so the sum of squares for the model, we also called for the regression, right? It is called SSR, right? For the error, we call it SSE. So we have SSR plus SSE equals to SST, right? So then in this case, this is SSR, right? This is SSE. These two sum together equals to SST, right? So then in this case, we say the total is this much. Then what is SSE? Will be the total minus the SSR. So then you have 77 something. All right. So then after that, we say next column is called the mean squares, right? So when we talk about mean squares, it's just the sum divided by the degree of freedom, sum divided by how many of them, right? So then in this case, we have MSR, which is SSR divided by the corresponding degree of freedom, K, right? And then we also have the MSE for the air, the same thing. We have the sum of the air divided by the degree of freedom, n minus 1 minus K, right? So then the next one will be the F ratio, right? So we have the F test statistics, which is MSR divided by MSE, right? So then we said here is MSR, this is MSE. So take the ratio and then you have 1364 something. All right, okay, so we are done with a ANOVA table. Then let's talk about this R square. So how to get this R square? In the formula sheet, we do have the R square formula, right? So it is SSR divided by SST. So the point is, which one is SSR? SSR is here, right? So which is sum of squares for the regression divided by the total sum of squares. End up with 0.993. All right. So the last one is this blank. right? So this is the t ratio for the experience. So the t ratio tells you the t-test statistic, right? So then we do have the formula for the t-test statistics, which is the b divided by the standard error of the estimate, right? So actually this is the b for the experience divided by the standard error of this estimate, right? So that will be this, right? Which is 71 something. All right, okay, so the first question, the next one. Based on the above output, state the sample prediction equation for this analysis, right? So then in this case, we say, right, so since you are writing the equation for prediction, of course, you want to use the parameter estimates, right? So that you have y hat equals to, let's say it keeps 3 decimals, 0.683, and then plus 0.5582 times GPA, right? And then plus 2.217 times experience, and so on, right? Okay, so number of independent variables equals to, so that means independent variables is the same thing to ask about how many predictors do you have, right? So that would be 4 of them, right? Some of you answer 5. That's because you count the intercept into it. But remember, the intercept is not a variable. The intercept is a starting point, right? It is not a predictor. We can also look at the degree of freedom for the model, right? So it is the K, which is the number of predictors in your regression. All right, so then next one, perform the overall significance test for this model. So that means we want to test whether the whole model is significant or not, right? So then in this case, what is the null hypothesis? What is the alternative hypothesis? We say the null hypothesis should be the model is not significant, or we say not meaningful, right? Alternative hypothesis is the model is significant or meaningful, right? So then in this case, for what case the model is totally not significant, that means none of the predictors affect the response variable, right? All of these predictors are not significant, right? Do we need to test all of these predictors one by one? No, right? So we do have a test so that we test all of these predictors at the same time, right? So all of these beta equals 0. And alternative hypothesis, remember, we don't require all of them not equal 0. We just need to make sure at least one of the beta not equal 0. All right, so now since we are testing about all the betas at the same time, then what we have for the test statistics, F or T, should be F. Right, so we have F test statistics. So if you go to the above output, right, so you should already got your F ratio here, which is your F test statistic. All right. And then what is the degree of freedom for this F test statistic? Right, so even though in the exam I didn't put any credits off for this part, but remember your F test statistics equals to MSR divided by MSE, right? So then we say for the ANOVA table, MSR has the degree of freedom, right? MSE also has a degree of freedom, right? So that's why we say the F test statistics has 2 degree of freedoms in this case. So that will be the degree of freedom of 4 and the degree of freedom of 41. So we have 4 and 41 as the degree of freedom. All right, so we call this is the numerator degree of freedom, and we call this is the denominator degree of freedom. All right, okay, so then let's continue. So what is the p-value? we have the F-test statistics, then the p-value is following, right? So then less than 0.0001. So what is the conclusion? That means your p-value is super small. We reject the null hypothesis. We have enough evidence to say the model is significant. The model is meaningful. All right. Okay. So then next one. Identify and interpret the meaning of R squared using the context of the problem. Right. So we want to interpret the meaning of R squared. All right. So first, what is the R squared? We just got it, right? R squared equals to 0.993, right? So then how to interpret this value, right? Some of you just say, okay, from this R squared, it shows a strong linear relationship, right? That is not the interpretation of this value. It's just that this value tells you what happened, all right? So then what does this value mean? That means 99.3% of the observed value in Y that can be explained by the predictors, right? So in context of this problem, what do we say? That means 99.3% of the variance in performance can be explained by the regression based on the GPA, work experience, certification, and number of absence. All right, okay. So then next one, perform a complete hypothesis test about the coefficient for GPA with four-step p-value approach. All right, so then the first step, hypothesis. Right, so now we are testing about what? We are testing about the coefficient of GPA, right? So of course we are testing about beta GPA, right? But what we want to test about, we say we test about equals to 0 and not equals 0, right? So then in this case, you want to use the t-test or you want to use the f-test. Say, when do we use f-test? When we test all of these betas at the same time, right? But now you are not testing about all the betas. You are testing about just one beta. So we don't use f-test. We use t-test, right? So where to find the t-test statistic for GPA? So of course, we go to the parameter estimates table, right? And then go to GPA row. And then this t ratio just to tell you the t-test statistics, right? And then the following one is your p-value. So now your p-value is 0.4536. Then what is your conclusion? Your p-value is super large, right? We failed to reject the null hypothesis. That means what? That means the GPA is not significant, right? But remember, this is in the multiple regression. What we say? We say with all other predictors already in the regression, right? Adding GPA doesn't have significant contribution to the regression. All right, okay, so then next one. Assuming that the 95% confidence interval for the coefficient of absence is obtained as negative 301 to negative 1.95 by jump, then interpret is this interval. Right, so now we are talking about the coefficient of absence. Right, so that means what? That means we are talking about how the absence affect the y, which is the performance. Right, so then in this case, that means when the absence increased by 1, right, then the y, which is the performance, will, so the whole confidence interval is below 0, right? So the performance will decrease by how much? By 1.95 to 3.01 units, right? And then remember, this is in the multiple regression. Whenever you talk about one single prediction, you always need to get all others fixed, right? With other predictors constant, or say fixed. All right, okay, so then next question. Assume that the 95% confidence interval for the coefficient of GPA is obtained as this much. All right, so again, this is about the coefficient for GPA. Then does this interval obtained in H have consistent conclusion with this hypothesis test in F? What do you think? What is the conclusion in hypothesis test in F? It's here, right? So we say what? We say GPA is not significant. With other predictors already in the regression, adding GPA doesn't have significant contribution to the regression. And from here, the confidence interval, you can see that it's from negative to positive. So 0 is inside of the confidence interval. That means sometimes GPA will decrease the performance. Sometimes the GPA will increase the performance. So is that consistent? Yes, right? They are consistent because in this case, the adding GPA doesn't have any contribution to the performance, significant contribution to the performance, right? Not increase, not decrease. All right. Okay. So then problem number 2, please refer to the attachment for the output of this problem. Right, so suppose the sales manager of a company wishes to evaluate the performance of the company's sales representative. The manager feels that the sales performance can be reasonably measured by the yearly sale of the company's product in the representative's sales as the response variable, right? So that means the sales will be my response variable, right? So he feels that the sales performance depends on some easily measured independent variables, right? So then the regression analysis is performed based on a randomly selected sample, and output is provided in the attachment labeled as model A. So let's look at model A, right? So this is the model A, right? So from the model A, what can you see? So from the parameter estimates table, you just have intercept and the accounts, right? So now let's come back. So the regression analysis until here, right? Where the sales is in hundreds of dollars, the sales is modeled using the number of accounts handled by the sales representative based on a randomly selected sample, right? So now write the least square prediction equation for this analysis based on the output. Again, I want you to give me the equation for prediction. So of course, we want to use the parameter estimates table, right? So will be these two, right? So then is that easy? Right, so that will be y hat equals to, that's the intercept. And then times x, right? Intercept and the b1 times x, right? So what is the x? X is the number of accounts, right? So this is my suggestion. Whenever you have this equation ready, right, you always just mark as much as you know about it, right? So for example, X is number of accounts, Y is the sales, right? And we also know the sales is in hundreds of dollars, right? So that in the future you don't get confused. All right, okay, so then based on that, identify and interpret B1 in context. So which one is B1? This is B1, right? So that means how to interpret that? B1 is the slope, right? So that means when, in general, that means when x increased by 1 unit, right? The y will increase by B1 units, right? So then in this case, that means what? That means when the number of accounts increase by 1, then the y, which is the sales, will increase by 21.72 units, right? So here sometimes some of you got confused. So we say the sales will increase by 21.72. Remember units, it do have the units in hundreds, right? You can either just bring it together, right? 21.72 hundreds, or you can directly change, say, okay, the sales will increase by $2,172. It doesn't matter which way, but bring the unit with it. That's it, right? You can see that it doesn't affect anything in your analysis. It just affects your interpretation or conclusion at the end when you talk about the sales. All right, okay, so then number 3. Are the regression assumption met? Right? I want you to explain clearly in detail reasons and reference to the appropriate name of the plots, right? So using only graph number doesn't get credits, right? So that means first you need to show me what are the assumptions, right? So for regression, we totally have 4 assumptions, right? The first one, linearity. Next one, the independence. Next one, equivariance assumption. Last one, normality assumption, right? So for linearity assumption, how you can check it? We look at the scatter plot, right? Okay, so now which one is the scatter plot? Which graph is the scatter plot? The first one, right? The scatter plot should be x versus the y, right? Does it has linear relationship? Yes, right? So then, yes, it has a linear relationship, right? Okay, so then independence. So that means we need to check whether the sample is randomly selected. So it is based on the randomly selected sample, right? So good, right? So what about equivariance assumption? What plot do we need? We need to use the residual plot, right? So then from the output, which one is the residual plot? We say the residual plot is the residuals versus the predicted y, right? So it's the predicted y versus the residuals. And then we want to check whether the residuals are equally distributed around the 0 line. So is this true? Yes, right? So equally distributed, all right? Last one, normality assumption, right? So which one? Graph 3, right? So then what is the name of this graph 3? It is called the normal quantile plot, right? So actually from this plot, you can also use another one, which is for this histogram, right? Histogram of the residuals also work for the normality assumption, right? So you can also use the histogram. Either way is okay, right? Is this good? Yes, because it is quite normal, right? It is quite normal here, and also in the normal quantile plots, the residuals follow the middle straight line, right? And then, yes. Okay, so now the assumptions are good, so I want you to make the prediction for the yearly sales. Right, so whenever you use the prediction, you want to make a prediction, of course, you want to plug in the values into your prediction equation, right? So that means you want to know what is the value of x so that you can plug in, right? So then we say for a cell representative with 120 accounts, right? So that means you have 120 accounts, right? So then just plug into this equation, right? Some of you got confused and changed this to 1.2 or even 12,000, something like that. Remember, this 100 is the unit for the sales, is not the unit for the number of accounts. All right, okay, so we'll just plug in the 120 into the regression, and then after calculation, your y is 3315.72. All right, then remember I'm asking about the prediction for the sales. Remember the sales is in hundreds of dollars. So this is just how many units do you have. So the real sale, the prediction of the sale is 3315.72 units, or we say hundreds of dollars. Or you can directly just change this to $331,572. Either way is okay because it only affects the sales. All right, okay. Let's continue. All right, so then next question. A sale representative under review has 120 accounts with sales of this much. Now find the residual. So how to find the residual? The observed y minus predicted y, right? So observed y this much, predicted y this much, right? So then you have the residual. Or if you use this one, that means you want to change this to 3,200 and then you take the residual, right? You need to keep the units the same. All right. Okay, so then does the sales representative over or underperform? So we say the observed y is lower than the predicted y. So that means underperformed. Okay, so then next question. Assume 95% prediction interval with 120 accounts is this much. Did the sale representative from the part E, which is from here, perform a reasonable level, and explain why not? And why not? All right, so from number E, what is the real observed Y for the sales? 32000, right? $320,000, right? But the predicted y is this much. The confidence interval for the predicted y is this much. But remember, the y is in hundreds, right? So that means what? That means the real cell, the predicted cell, should have the range of 2950 and sorry, in hundreds, right? So that would be 2 more zeros, right? And then to 368100, right? So this is the true range for the cell. Now you can see that $320,000 is in the interval. So that means even though it is underperformed, it is still reasonable, right? Okay, so now let's talk about problem 3, right? So refer to the model B output to answer the following questions. Model B shows a new model for the sales performance. This analysis includes an additive variable, which is the time on the job. All right, did adding time to the model improve it? And provides 3 supporting reasons with the detailed specific values. All right, so how to compare models? We have model A with number of accounts, model B, right? So let's look at these two models. Right, so model A and model B. So now we see that model A includes accounts, right? Model B, we have one more predictor added, time is added into the model, right? So now we want to know whether the model B has improved, right? Whether adding time to the model improved the regression, right? So how to compare these two models? The first one, of course, we want to compare the adjusted R square, right? So if you look at the adjusted R square, we have 0.55 and 0.53. So which one is larger? This one is larger, right? So that means model A is larger. So that means model A is better, right? Can we use R square? No. All right. Okay. So then what's the next? We say adjusted R square always pair with MSE, right? Adjusted R square, that means the better version of this, better aspect of this regression, right? We also need to compare the bad aspect of this regression, right? So that means the smaller MSE, the better, right? So then in this case, let's say where is MSE for model A? For the air, right? So MSE, right? And then this is the MSE for model B, right? So which one is smaller? A is smaller, right? So again, A is better, right? Okay, so then for the third proof, right? So normally it's optional, but for this question is asking for it. So what you can use? The first one, you can use the F ratio, right? F test statistics. We say the higher F test statistics, the model is more significant, right? So then for model A, you have 30, model B, you have 14. So which one is better? Of course, A is better, right? Of course, you can have the fourth one. So let's look at the added predictor, right? So this one has accounts. This one you have one more predictor added. But if you look at the p-value for this added predictor is 0.57. So how do we make the conclusions about the big p-value here? We say with accounts already in the regression, adding time doesn't provide actual contribution to the regression, right? So that's why this fourth one will be the added predictor time is not significant, right? It is not helpful to the regression. Right, so now in this case, of course, again, A is better. Then let's come back to answer this question. So did adding time to the model improve it? Of course, no, right? Model A is still better. All right, okay, so then last problem, right? So refer to the Model C output to answer the following questions. So the company that produces Fresh, which is a brand of liquid laundry detergent, wants to make revenue projections by predicting the demand for the detergent, right? They gather the data and then by random sampling, right? And then for model 3, for model C, so let's look at model C. So here is model C, right? So from model C, we have these variables defined, right? The first one, right? So it is called demand. It is the demand for the large size bottle of Fresh in hundreds of bottles, right? And in the sales period, and it was told that it is a response variable, right? So demand is your response variable Y, right? And then next one you have the price difference, right? It is the price difference in dollars between the price of Fresh and average industry price of the similar detergent during the sale period. Right, and then ADVEXP, this is the company's advertising expenditure. It is in large numbers, right? It is in hundreds of $1,000 to promote the Fresh in sales period, right? And then next one is called the marketing ad campaigns, A, B, or C. So when you look at this variable, it's kind of weird, right? Because it is not real numbers, it's just A or B or C. So that means this variable is a categorical variable, right? With 3 categories, right? Okay, so now let's look at the question. So it says refer to the output of model C. Okay, so now let's look at the model C. So in this case, we have the intercept, we have the price difference, a venture advertisement expenditure, right? And then we have A and B. All right, so now let's come back to the question. Please describe in details about how did he or she add this variable, which variable, the marketing ad campaigns into the regression. What is this variable? This categorical variable, right? So once you have a categorical variable, how would you add this into the regression? We create dummy variables, right? But if we don't have the output, we can randomly choose one as the base, right? But from the output, both A and B are added into the regression. So where is C? Why C is missing? We say C is the base, right? And we set C as the base so that we create a dummy variable for A, we create a dummy variable for B, right? So then how we define these two dummy variables? We say for A, if we use the campaign A, then this variable equals to 1, 0 if we don't use the A, right? Again, for dummy variable for B equals to 1 if we use B, otherwise 0, right? So this is how we define the dummy variables, right? Okay, so then number B, based on the output, make a prediction of the demand, right? So I want to make a prediction of demand for detergent if the company decides to use campaign B with this much for advertising expenditure and the price difference between the fresh and the average price is set to be $5. And be careful with the units. All right, so then in this case, that means I want to make the prediction for demand. Whenever you want to make a prediction for the response variable, how can you start with, or what is your first step? What is your first step? Of course, you want to state your prediction equation so that you can plug in the values, right? So then the prediction equation, we need to look at the output and then use these coefficients to write the equation out, right? So that means y hat, which is the sales, or sorry, not sales, the demand, right, equals to 4.48 and 1.64 times the price difference and 0.58 times advertisement expenditure, and then minus 0.41a minus 0.18b, right? So it will be these coefficient times the corresponding predictor. All right, okay, so now it's time to plug in the values. But before you plug in the values, remember each predictor has or each variable has different units, right? So we say the demand has the unit of in hundreds of bottles, right? So in hundreds of bottles, right? And price difference, let's say the price difference is in dollars, right? So no big deal, right? Advertisement is in hundreds of $1,000, right? So this is in hundreds of $1,000, right? And then A and B are dummy variables. All right, so now we are ready for predictions. Let's plug in the values for each, right? So what is the price difference? We say the price difference between fresh and the average price is set to be $5, right? So then just plug in 5 into it, right? And then what about the advertising expenditure? We use this much, right? So that means 350.000, right? So we have these amount of money for expenditure, right? So then what do we want to plug in? Remember, it has the unit of $100,000. Now you have $350,000. Then how many units do we have? 3.5, right? So we just plug in 3.5. And what about A and B, these two dummy variables? We say we use the camping B, so that means B is 1, right? A, we didn't use A, so then 0. So now you have all the values, and then just plug in and calculate. So after calculation, you should have this 14.53. But remember, the demand is in hundreds of bottles, right? So then you can just bring the units with it, or you can just change to the detail number of bottles. All right, okay, so then last question. Identify and interpret the meaning of B3. So which one is B3? This is B0, B1, B2, B3. So I'm looking for the coefficient for A, which is negative 0.41, right? So how to interpret this? First, this is a dummy variable, right? So for dummy variable, we always compare to the base, right? So then in this case, compare to the campaign C, using campaign A will decrease the response variable, which is decrease the demand by how much? By 0.41 units, but units is in hundreds of bottles, right? So it will decrease by 41 bottles, right? Is this done? Not yet. This is a multiple regression with price difference and expenditure both fixed. All right. Okay, so then the last question, actual credits, right? So it's the problem for continued. I want you to state the regression equation for predicting demand when we use the A campaign or B campaign, right? So what's the difference? We say everything else will be the same, right? We want to keep everything else the same. So that means what is the equation for Y for when you use the campaign A? So that's just a 4.48, 1.64, the price difference. Everything is nothing changed, right? Expenditure. But now in this case, right, when you use the A, that means A will be 1, B will be 0, right? So just left with negative 0.41, right? If this B, that means your prediction will be everything here will be exactly the same. But if you use the B, B will be 1, A will be 0. So here will be 0.18, right? So then what's the difference in demand? Everything else here is the same. Then the difference is just the coefficient difference, right? So negative 0.23 in hundreds. So that means the difference is just 23 bottles. All right. Okay, so that will be all for the exam 2. You can see that exam 2 is focusing on how you understand the regression and how you interpret, how you make the conclusions, right? So actually, just the 2 questions about calculating the predictions. Otherwise, you just need to understand all the details, the kind of understanding details. All right. Okay. So that's it, right? So be sure to start your review as soon as possible. So even though the previous chapters takes about 30 to 40%, but still they are important. You don't want to lose these 30 points or 40 points, right? Okay, right. So that's it, and good luck, everyone. Thank you for the whole semester.